On this problem, we are asked how many ounces of each solution should she use? So that lets us know what our variable should be. So we know that if we take the amount of solution A and add to that the amount of solution B, we should end up with 110 ounces. We also know that 65% of solution A is salt. And if we add to that the amount of salt in solution B, then %80 of the total amount should be salt. So once again, we have a system of equations. And so one way to take care of this would be the substitution method. So I will take this equation and solve for x or y. I'll solve for x. So I can now replace x with 110 minus y in the other equation so that I end up with this. So now it's time to solve for y, and we should get rid of the parentheses. Now we can combine like terms. And finish solving for y. So the amount of solution B is going to be 66 ounces. So how much solution A will there be? Using this equation, I can replace y with 66 and solve for x. And x is 44 ounces. And that's how we do it. Since this problem involves distance, rate, and time, that means that we will use the dirt equation. Da, 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 da. But first, we must define our variables. Since we are being asked to find the speed of the water and the speed of the river, I will make x speed of the boat and y speed of the current or the river. Now, x is the speed of the boat in still water when it's not being pushed around by the stream. Using this equation here, we might set something up like this. You don't have to use these fancy boxes, but it's kind of nice. One row would represent going downstream and the other one going upstream. So we know that a motorboat travels 159 kilometers upstream. So the distance upstream is 159, and it takes him 3 hours. And going downstream is 824 miles or kilometers in 8 hours. Now the rate or speed going upstream and downstream is not explicitly given. However, we can deduce that, for we know that when a boat goes downstream, the speed of the boat will be however fast a boat normally goes, plus the speed of the current, because it's downstream. And when going upstream, the speed would be the speed of the boat minus the speed of the current, because the current is pushing back against the boat and therefore slowing it down. Now, since distance equals rate times time, I know that I now have two equations like this. So now I can solve the system of equations, but first I must get rid of the parentheses. At this point, I could do substitution or elimination method. I think I'll do elimination and multiply the first equation by 3 and the second by 8 so that I get the following system of equations. Now, when I add the equations together, the y's will cancel. And dividing by 48, I get 25 kilometers per hour. And X stands for the speed of the boat in still water, so that's how fast the boat typically goes. What about the speed of the stream? Well, we expect that it's probably going to be considerably less. So we just need to replace X with 25 in some equation. I'll use the second equation. Now at this point, I find that I'm going to get a negative answer. In fact, it's going to be negative 28 miles per hour or kilometers per hour. Well, that doesn't make any sense. It should not be negative. So apparently I've made a mistake. So now I have to go back and find it. Fortunately, we have to go a little ways back. When I added these together, I actually subtracted, which of course did not help. So going back, I get this. Dividing by 48, X is actually 78 kilometers per hour. I'll let you plug the 78 in for X into one of the equations, doesn't matter which, to solve for Y. But when you do, you should get 25 kilometers per hour. One more. For this one, we'll just use the explanation that Alex has provided. We'll start by defining our variables. And then we can make this fancy table to help us figure out our equations. It's not necessary, but it is nice. So the costs are X and Y. The interest rates are 0.07 and 0.06. And therefore, multiplying those together, we get the finance charges of 0.07X and 0.06Y, which all adds up to $398. So using the table, we get an equation of Y equals X plus 350. Or no, that's not from the table. That's from the information at the beginning of the problem. But we do know from the table that this that we get this equation right here. And so now, once again, no surprise, we have a system of equations made up of these two guys there. Since one of the equations already has a variable isolated, the author has decided to do substitution method and plug this expression in for Y, which we see right there. And then we solve for x, which is $2,900, and then substitute that in for x so that we can get y equals $3,250. That is how it's done.